Okay, I'm giving you next around please put your beginning music. Can you hear me? And how do you integration? And how do you okay, okay, I think I'm going to use my I'm happy to use the blackboard and I'm going to use my voice. And yeah, I will start. Okay, hello guys. Hi, good evening. So yes, welcome to the class. So we'll be starting with the technical check, guys. Come on, please take your technical check. Let me know if my voice is audible to everyone and if the blackboard is visible to everyone. Hi Kriti, good evening. So hi Abhishek, Kavya. Okay, there are many few students. Okay, we'll wait for more students to arrive. Yes, bro, on the way. So okay, so hope guys everyone try to revise yesterday's class and any doubts you got, guys? Any doubts from yesterday's problem, the last problem, or any problem you had? Any doubts in the previous class? So guys, everyone, please take your technical check. Guys, come on, that's important for me to know whether you are able to hear my voice clearly and if the blackboard is visible to you guys clearly. Okay, so hope everyone are here and everyone is able to hear the voice and everyone is able to see the blackboard clearly. Please take the oath. So in our previous class, okay, so I'm waiting for more people to respond. Guys, this is very important, guys. Come on, please respond. Come on, guys. Response is very important. Okay, thank you, bro. Then we'll start with the class. Yes. Excuse me. Okay, I'm going to end the poll for you guys. Okay, so in our previous class, we discussed about electric field. Sorry, the energy stored in the capacitor. So we discussed about energy stored. So what was the expression, guys? Come on, tell me what was the expression for energy stored in a capacitor? In a capacitor, what is the energy stored? I want every one of you to answer. YouTubers, please try to answer. So we try to derive an expression for energy stored in a capacitor in previous class. So there were three expressions. So how did we start? Like what is the expression for energy stored in a capacitor? Yes, correct, Abhishek. So it was, yes, we know we had two parallel plates. Say we had two parallel plates. One plate was charged with plus Q charge, other plate was charged with minus Q charge, and these two plates were oppositely charged. Since they were opposite in charge, they attracted, right? So I had to do some external work. So I had to apply some external force. Then this external force was saved as or stored as potential energy in between the capacitors, right? In between the space or in between the plates of the capacitor. Okay, so that energy was given by E is equals to half CV square, right? So there were three formulas. One is E is equals to half CV square. What is the other form? So I can say E, I can use potential energy U. So what was the other two forms? U is equals to, come on guys, tell me what were the other two forms? So before this, we had one more form. Potential energy stored in the capacitor is given by U is equals to. Okay, if you don't answer, I can. I mean, if you answer, guys, it will be very good for me, so that we can have an interactive session. Otherwise, see, it will be monotonous. Only I will be speaking and you won't be answering. So that is not good, right? So please answer, please respond. See, you guys are the energy of the class. If you be like this, then there won't be any energy in the class, right? Come on. Yes, correct, Abhishek. Only Abhishek is answering out of many 17 plus students. So others, please try to answer. Come on, guys. Yes. The second form was, or the previous form was, say if we have a charge that is Q square by 2C. Okay, hi YouTubers, cool, superb. Awesome, guys. Bhargav, correct. Ramakrishna Reddy, Krishmodi, Priyanka, Lakshmi, Likita, and Devika Rani. Thank you. Thanks for response. Yes, the second form was this: U is equals to Q square by 2C. Then what was the third form? One more form. Yes, exactly. U is equals to half Q into V. So these were the three forms of the same expression. Okay, this is the same expression. Then we solved some problems based on these. So in today's class, we'll be starting with a different approach. So guys, what do you mean by density? Please be active, guys. Come on. What do you mean by density in your physics or in anywhere? So what is meant by density? So density in general, you might know it as what? Yes, correct, Abhishek. It is mass upon volume, right? So if you have some mass, yes, correct, in my Prajwal, correct. So if we have some mass spread over a volume, or given if I have some container, so what does density mean? If I have some container and this container has some volume V, in this volume V, if I fill something, say if I fill air, if I fill air, what is the weight of this container? Is it more or less? Say I have a container, maybe a plastic bag. Okay, it has some volume V. Say if I fill air with this, will it have more mass or less mass? Will it have more mass or less mass? Mass will be less, right? So what can I say about density? Density will also be less. If I have, instead of air, if I have water or any liquid, what happens? If I have any liquid, my mass will be automatically increasing. So my density of that material also increases. That is meant by density, right? Now, if that is density, what is meant by energy density? So what do you think energy density is? So you know density, you know the meaning of density. Here we are going to discuss about energy density today. So what do you meant by energy density? Energy density andre enta? What is meant by energy density? So which type of energy are we talking about here? Yes, exactly, Dhanush. Super. Exactly. So energy which we are going to talk about here is the electrostatic potential energy. Okay. We are going to talk about electrostatic potential energy. So energy density means exactly it is electrical energy or electrostatic potential energy. I'll write EPE. Okay. Short form of electrostatic potential energy. I'll write EPE per unit volume. So electrostatic potential energy per unit volume. Okay. This will be nothing but my energy density. So we are going to discuss about the expression for energy density of electrostatic potential energy stored in a capacitor. Okay. Sarina. So, okay, I want to repeat again. So this means, see, energy density means, say I have some electrostatic potential energy stored, right? In a capacitor, I have some electrostatic potential energy stored. Okay, we know density is nothing but mass by volume in general, but here energy density means electrostatic energy, potential energy spread over unit volume. For every unit volume, say for every given volume, how much energy is spread out or how much energy is distributed, that we are going to discuss in this part. Okay, so we are going to discuss about the energy density in capacitor. So what we have to consider? We'll consider the capacitor. So potential energy stored in a capacitor is in term. So we are going to write this electrical energy density or potential electrostatic potential energy density in terms of electric field existing between the plates. So we know that inside a capacitor, say we have a capacitor of two parallel plates. Say one plate is charged with plus q charge, other plate is charged with minus q charge, and there exists an electric field E between them, right? So which was separated by a distance d, there exists an electric field E between them. So guys, quickly tell me, where is my positive and negative charges? So this is one curious question I had. So this is just for my confirmation. Please tell me, where are these positive and negative charges in this capacitor representation? inside the plates or inner surface of the plates, outside the plates, or on the plates, spread out through the plate. Correct, Rakesh. Right, Alvam. So these positive and negative charges are only on the inner side of the plates. They are not on the entire plate. They are only on the inner surface of the plates. Only on these inner surface of the plates. So I have net positive charges here and net negative charges here. Right? So there exists an electric field between the plates. This electric field stores some energy. This electric field has some energy, that is the electrostatic potential energy. So we have to derive how much energy is there. So the electrostatic potential energy or electric potential energy stored in the capacitor is given as, we just saw now, that is U is equals to half Q square by C. I'm going to consider this formula. Okay. Now, now, say if I want to consider, say if I know the surface charge density, we know the surface charge density given is sigma is equals to Q by A. Hold on. So if we want to represent this charge in terms of surface charge density, we can represent it as Q is equals to sigma times A. Correct? Now, once we substitute this, expression of energy density, electrostatic potential energy will become U is equals to half sigma A square by C. Okay, so this is the expression which we get. So guys, come on, tell me what can we do next. So we want to have an interactive session, right? So please let me know what can we have next. So in place of what is the next step? What do you think would be the next step to go? Help me solve this. Okay. So we know that the capacitance equation, parallel plate capacitor equation, what is the capacitance equation here? So we'll substitute the value of capacitance. So what is it? C is equals to epsilon naught A by D. So we'll put the value of C there. No, Hari Prasad, it's for parallel plate capacitor only. It's not Q is C is equals to Q by V. Okay. Yes, it is C is equals to epsilon naught A into D. Sorry, epsilon naught A by D. Now we know the electrostatic potential energy expression will now change as E is equals to, sorry, U is equals to half Q square, sorry, half sigma into A whole square D by epsilon naught A. What will happen next? So I want to introduce, so what I wanted to introduce, I wanted to introduce electric field E in this. So what can I do? So guys, tell me what is the expression for my electric field? What is the expression for my electric field E for both the plates of excuse me, for both the plates of capacitor? What is my electric field E given by? Exactly, Tejas, super. So it's nothing but sigma by epsilon naught. Correct, Prajwal. It's sigma by epsilon naught. Correct in my. Yes. Priyanka, it was sigma by epsilon naught, not kq square, kq by r square. So this was the expression for electric field, right? So I have to introduce this here. Can I? How can I introduce that? So I have to introduce electric field E, that is sigma upon epsilon naught here. Can I? How can I do this? How can I achieve this? So I can do that by multiplying and dividing by epsilon naught. Okay. So I can do that by multiplying and dividing the equation, above equation, by epsilon naught. So what will happen now if I multiply and divide by epsilon naught? Check out. So we'll get U is equals to half into sigma A square D by epsilon naught A into epsilon naught by epsilon naught. Now, if you try to multiply these two, what will you get? So you'll get something like U is equals to sigma square A square D into epsilon naught by 2, I mean, half into sigma square A square D epsilon naught. This epsilon naught is multiplied here, divided by epsilon naught square. So we know electric field E is equals to sigma by epsilon naught, right? Since we know electric field E is equal to sigma by epsilon naught, can I equate this much? sigma square by epsilon naught square as what? Can I equate this to E square? Can we equate this to E square? Yes. So we'll substitute that. I hope everyone is trying to write down parallelly. So substituting all the values, say substituting sigma square by epsilon naught square as E square. So we'll get the expression of electric field, electrostatic potential energy as U is equals to half E square epsilon naught into A into D. Now guys, tell me what is my A into D? What is my A? What is A? Yes, exactly. A into D is nothing but my volume. Here, A is my area and D is my separation distance, right? So the length times area. So we know volume is nothing but length times area. So here my length is D and A is area. So I will get A into D as nothing but my volume of. So what volume is this now? Say everyone said this is volume, but what volume is this? Okay. Yes, it's the volume. So this is the volume of the space between the two capacitors. So two plates of capacitor, whatever the area of cross section A I had and the length separation distance D I have. So this area of cross section times this D. So this entire thing, this entire volume, so this space which is highlighted with blue, in this volume, my electric potential energy will be stored. So electrostatic potential energy will be stored. Okay. Now, so this is the expression for electrostatic potential energy stored between the plates of the capacitor in the volume, so where A into D is volume of the capacitor, or volume between the space, or volume of the space between the two plates of the capacitor. Okay. Ega. So what can we conclude with this? We can conclude that the electric potential energy is stored in between these. So we know this, right? Now, what can we do next? So what do you mean by electrostatic potential energy? Now, sorry, electric energy density. So we come to this derivation. The electric potential energy stored is given as we know U is equals to half E square epsilon naught into A times of D. The electrostatic energy density, the electric energy density now can be given as E is equals to, sorry, U is equals to capital U divided by A into D. So now if we divide this potential energy by volume of capacitor, we get the electric energy or energy density of electric field between the plates of capacitor. So this is the expression for, yes, electric field. Now, yeah, my volume A into D in the denominator, A into D in the numerator gets cancelled. So I'll be getting this expression mu is equals to half E square epsilon naught. So guys, this is the expression for energy density or energy electric field, energy density of electric field between the plates of capacitor. Okay. Hope everyone have understood this derivation and have written somewhere. Written in your book. Okay, this derivation might be asked in your CBSE test. Please be prepared with this. Okay. So this question might be asked in your CBSE exam, in your 12th board exam. Okay, everyone. Hope this is understood. Please let me know if you have understood this. All the steps. So how to derive. So if you want, I can give a quick recap of what we have studied. So first we took the expression mu is equals to half q square by c. So with this expression, yes. So with this expression, so we took u is equals to half q square by c. In this expression, we considered the surface charge density sigma as q by a. From here, I can write my q as sigma times a, right? So now I'll substitute this value over here. What will I get? U is equals to half sigma a whole square. by C. I know what is my C. C is epsilon naught A into D, right? So I'll write that. So 1 by C is epsilon D by epsilon naught A. Now I want to introduce electric field here. So in this step, I'll multiply and divide this equation with epsilon naught. So what I'll get, U is equals to half into sigma A square, sorry, sigma square A square by epsilon naught square into D epsilon naught. From here, my A square and A get cancelled. So I'll be remained with, so I'm completely eliminating these. So I'll be remained with A into D epsilon naught. So what can I write this sigma square by epsilon naught square as? So we know electric field E is nothing but sigma by epsilon naught. Say then sigma square by epsilon naught square can be written as E square. So from here I get my electrostatic potential energy as half into E square into AD times of epsilon naught. So here my A into D is nothing but my volume. Okay. Now, now if I divide this potential energy by volume, I'll get the electrostatic potential energy per unit volume. That is nothing but my electric energy density. So this is the expression for energy density. So yeah, the remaining thing is this. So this is the expression for energy density per unit volume. Okay. So I hope this is understood. Please click on it if you have understood. Manohar. Yes, guys. Guys, everyone, please. So Hari Prasad, we can do without multiplying and dividing with epsilon. So yeah, we can do that also. So, but that has some complications, Hari Prasad. So I'll try to go with simpler way. Okay, now guys, this expression. So guys, I hope everyone have got this. Please give a confirmation, guys. Manohar, confirmation ಕೊಡಿ. ಅರ್ಥ ಆಗಿದ್ಯಾ ಅಥವಾ ಇನ್ನೊಂದ್ಸತಿ ಹೇಳ್ಬೇಕಾ? Hello. Okay, cool guys. So next, everyone might have, yeah, everyone have understood. Now this expression, guys, this expression is very interesting. Okay, so this expression is not only for electric field energy or electric energy density between the plates of capacitor. This is also true for any surface. This energy density expression is true for any electric field. What do you mean by this? Okay, what is the meaning of this? Can anyone say me? What is the meaning of this? So they have said the electric potential or electric energy density, which the expression we got, U has half into E square epsilon naught, right? So this expression is true for any field or any surface where it has electric field. So what do you mean by this? Yes, it has, Karthik. So we'll study about that in detail in our dual nature of particle chapter. Okay, it comes in our modern physics. So we'll study that in detail. So we don't introduce that here. So it may create confusion. So I'm not introducing that here about the photons. We'll discuss that in a separate chapter where we have the particle nature of matter. So we'll discuss there. Okay. Yes, it doesn't have. ಅದೇ ಅಲ್ವಾ ಹೇಳಿದ್ದು. We'll discuss for that you have to know how photoelectric effect happens and all. So that's a separate discussion. We'll keep the discussion in future. So Raj Lakshmi, to introduce the electric field, ma. So I wanted to introduce that expression in terms of electric field. So I had multiplied and divided by epsilon naught. Okay, so guys, the question which I asked was coming back to this. The energy density expression is true for any electric field. This means in any region with the electric field. So wherever the electric field has, wherever we see the electric field between any two particles, then the energy stored in that electric field is given by the same expression. Okay, this same expression gives talks about the energy stored in that field. Okay, so we are going further. Hope this is understood by everyone. Please click on yes or please confirm if you have understood this. Guys, respond please. Okay, cool. Yes. So I have a question for you guys. So a parallel plate capacitor of capacitance C is charged. So this question, please go through it. So a parallel plate capacitor of capacitance C is charged to a potential difference V and charge is Q. The energy stored in between the plates of the capacitor is E. In this situation, say initially had a capacitor, parallel plate capacitor. So area of cross section is A and separation distance is T now. So this capacitor has a capacitance C that is equal to epsilon naught A by D, right? Now this capacitor stores some energy as electric fields between them as E. If E is the electric energy stored, now what happens? Now the capacitor is disconnected from the battery. So it was initially connected to a battery. Now this battery is disconnected. So and the separation between the two plates is reduced. My D is reduced. D is reduced. Now what happens to the energy stored in, or what happens to the new energy stored in between the plates of capacitor? So this is the question. So I'm going to launch the technical check. I mean, sorry, the MCQ poll. Please answer in the MCQ poll. Yes. Hope any. I hope you guys have understood the question. Any doubts in the question? Please let me know. So if you want confirmation of answer, you could also answer in chat box. So guys, please, everyone else can answer. I mean, all students in YouTube can answer in the chat box. Karthik Gowda, check your answer. Tejas correct. Prajwal, check your answer. Rakesh correct. Hariprasad, check your answer. Priyanka correct. Dhanush, no, check your answer. Prajwal, check your answer. So use the formula which we just learned, guys. Or you can use any other formula for energy stored. You know, energy stored is E is equals to half CV square. You can use this formula too. Yes, Manohar, correct. Yes, Prajwal, correct. Anusha, check. So C is equals to epsilon A by D. So guys, yeah, I hope everyone might have answered. So we'll discuss the answer. So yes, I'm going to end the poll. So yes, most of you have given me the right answer. See, listen. So initially the parallel plate of yes, correct, Priyanka, Lakshmi, Ramakrishna, Uday, correct. So what happens? A parallel plate capacitor of capacitance C is charged to a potential V. So I have a potential V between the plates of capacitor, and charge is Q. Q is a charge, and V is the potential. The energy stored between the plates of capacitor is E. In this situation, okay, now the capacitor is disconnected and the separation between the plates is reduced. So you know that C is equals to, or yeah, we know Q is equals to C into V. Now guys, my Q is constant, right? Say I have some charge Q. Say what is my C capacitance equation? C is equals to Q by V. Hola. Can we say my capacitance equation is given by C is equals to Q by V? Yes, yes. Now what happens? Some energy is stored in this. So that energy is maybe half CV square. Okay, my energy stored is half CV square. Now what happens? So I have same amount of charge, same amount of potential. Okay, so suddenly, say my plates, the C is equals to epsilon naught A by D. We know this, right? Since suddenly my reduction, there is some reduction in distance, separation between the plates. What happens to C? What happens to C here? When my separation between the plates decreases, what happens to C? Yeah, capacitance, pa? Yes, C should increase, right? My C should increase. Or the say if C is increasing, so here with this equation, check with reference to this equation one, my capacitance increases as my D decreases, right? With respect to this equation two, if my capacitance is increasing for the same amount of charge, what happens to my potential? For same amount of charge, if my C is increasing, what happens to my potential? Potential decreases, right? So remember this, potential is decreasing. Now substitute same, put the same values in C, electric field E, sorry, energy stored in capacitor E. See, my capacitance is increasing one time, but my potential, since it's decreasing, as a square of potential. Say I have energy equation as half C into V square. If my potential is decreasing and it's the square term, so is the energy, no, it will not be same, right? Potential is decreasing, Danush. Say, for the same amount of charge, if my capacitance increases, my potential should decrease. Alva, are you getting this? Yes. So my since my potential is decreasing, see my potential is decreasing, but my capacitance is increasing. So you may say, sir, capacitance is increasing, potential is decreasing. So energy should remain same. How many say this? Is it possible? Like, see here, in this case, my capacitance is increasing, potential is decreasing. Sir, energy should remain same. How many say this? How many say energy should remain same? Should the energy remain same? Respond, guys. Hope my voice is audible, right? So my energy obviously will not be same because see one time, see if you see here very carefully, my capacitance is increasing, yes, a little bit, but my potential is decreasing a little bit. But when it decreases a little bit, it's as the square, right? Potential is two. It's decreasing the square times. Capacitance is increasing one time, but potential is decreasing the two times or square times. So my overall energy should obviously decrease, right? In new case, when my capacitance increases, the potential decreases. In this case, my net energy or the new energy stored in between the plates will obviously decrease. Hoda. So option B is the right answer. Option B is the right answer. It will be lesser than initial E. So this is E dash. E dash will be so half C dash V dash square. E dash will be half C dash V dash square. So E dash will be obviously less than E. So any doubts in this, guys? How many did not understand? If you guys did not understand, let me know. Yes, Hari Prasad, that's what I was talking. Say, yes, see here C is equals to Q by V. If my C is increasing from this expression, from first equation, I know my C is increasing. Capacitance is increasing. Alva. So since my separation between two plates is decreasing, the capacitance increases. So we know the capacitance as C is equals to Q by V. So for given potential, okay. So I'm repeating, please listen. Say we have two expressions for capacitance. Which are the two? For parallel plate capacitor, we know C is equals to epsilon naught A by D. But they have mentioned, yes, for a parallel plate capacitor, the capacitance is epsilon A by D. It has some charge Q, and there is a potential difference V and charge Q. Using this, I can write my second equation for capacitance as C is equals to Q by V. Now, what they mentioned, so there exists an energy inside the capacitor that is given by E is equals to half C V square. Okay, so this is E is equals to half C V square. So this is the initial energy stored inside the capacitor. Okay, now what is happening? Now the capacitor is disconnected from the battery. Okay, and the separation distance, the distance between the two plates is decreased. Distance between the two plates is decreased. So obviously, what will happen? The capacitance will increase. Howda? So my capacitance is increasing. So since my capacitance is increasing, from second equation, what should I say? Since the capacitor is increasing, from second equation, what should I say? My potential will obviously decrease, right? Artha agila. How many did not understand? See, initially I had some separation. Say I had 10 charges, 10 positive charges, or say, yeah, I had some 10 positive charges, had some 10 negative charges in these plates, in between these plates for separation D. So there existed some electric field, uniform electric field E. Okay, there existed uniform electric field E. Now what I'll do, I'll increase this distance, separation distance, by some more. Okay, by some more. Now, yeah, though I have same amount of charge, my electric field, the distance traveled will increase. So as my electric field, in the direction of electric field, what happens? The potential decreases, right? Okay. Since my charge is same from this expression, since the charge is same, my potential should decrease to increase the capacitance. Okay, sorry. Here in this case, it's decreasing, right? Yeah, it's further decreasing. Okay. So my electric field will be this much, but my potential decreases. V decreases. So this new V will be called as V dash. So new capacitance will be called as C dash. So if you try to check the value E dash, that will be C dash times V dash square. Here my V dash is less than V. V dash is less than V and C dash is greater than C. Okay. If you try to substitute, so my V dash is square of the term. So when I have a lesser quantity which is squaring, it will become more lesser. When I have a single quantity which is increasing, it will be staying there. But when I'm squaring a lesser quantity, it will further reduce. It will further decrease its magnitude. So the net energy to overall energy will be lesser than the initial energy stored. Okay, guys. I hope all of you might have understood now. Yes, if distance increases, it will become opposite. So if distance increases, so what would happen if distance increase? Check that. Say if D is increasing, if D is increasing in the second case, so my C will decrease. If C is decreasing, my V will increase. Then obviously my potential should, energy stored should also increase. Okay. Okay, guys. I hope everyone have understood. Please click on. Let me know if you have understood, or let me know if you have not understood also. Please, since you have not responded me, I'm still here. Everyone, I hope everyone might have understood. Please respond. ನೀವು ರೆಸ್ಪಾಂಡ್ ಮಾಡಿಲ್ಲ ಅಂದ್ರೆ ನಾನು ಹಿಂಗೆ ಮುಂದೆ ಹೋಗೋದು. Okay, cool. Thank you. So hope that question was understood. Now, in today's class, we'll be discussing about capacitor as a device. So we have so far learned how capacitor, we have learned many things about capacitor, say what happens when a capacitor is connected to a battery, how it stores charge, so everything. So today we'll practically learn how a capacitor works. Okay. So I hope everyone are able to see this battery here I have a battery. So this is a Duracell battery. Say it has a net amount of total net amount of charges. So it has one set of positive charges on positive plate. I mean, the construction of battery is similar to that of a capacitor. So it has two plates. Even the battery will also have two plates, one positive electrode, one negative electrode. I hope this is learned in your chemistry. One positive electrode, one negative electrode, and it's kept inside a solution, chemical solution, right? So the electrical energy is stored as chemical energy inside a battery. Now, say if I connect a capacitor to this, say consider two plates of a capacitor. Say I have two plates. Now, what happens? What happens when I connect a battery to this? ಏನಾಗುತ್ತೆ ಹೇಳಿ? So what should happen when I connect a battery to this? Guys, I hope this is taught in your school, but please let me know if yeah, what happens in this case. Yes, capacitor gets charged. Which charge? Okay, let's see this animation. So I have the capacitor, parallel plate capacitor here. This capacitor is connected to a battery. When the capacitor is connected, you could see all the positive charges from the battery stores on the one end of the plates. So next, what happens? What should happen? All the negative charges of the battery will be on the other end of the plate, right? So there are two plates. So in these two plates, one of the plate has positive charges, one of the plate has negative charges, right? Now, yes, these two are one outermost end of this plate is positively charged, outermost outermost plate of this plate is negatively charged. Now, what will happen in this? In this case, what should happen? So we learned in our electrostatics, what will happen? So one end of the plate is positively charged. So what should happen to the other end? What should happen to the other end? Oi, attraction Lapa. Say if one end of the plate is positively charged, what should happen to the other end? Yes, it will attract all the negative charges. Okay, so it will induce. You remember, guys, it will induce. So there will be some induction force. So these positive charges will induce a negative charge, net negative charge on the inner surface of this wall, I mean of this plate, and these negative charges will induce a positive surface in this surface, in the inner surface of this wall, and there exists an electric field inside these plates of the capacitor. Okay, there exists an electric field inside the plates of this capacitor. So this is called as the polarization of plates of the capacitor. Okay, so this is how a capacitor starts working. Now what happens to the outermost? Say if you say, sir, always we say the plates out of the plates, I mean the outer surface of the plates will have zero net charge. Why is it? Why should it be zero? Guys, try to answer this. I hope everyone have this question. Everyone might be having this question in general. Sir, everyone says the outer plates have zero negative charge. I mean zero net charge, but you have not shown that. Everyone say the outermost surface has zero charge, but is it zero charge here? So it is zero charge, but how? Any idea, guys? So when we are comparing, when we are checking for the surface charge, right? When we are checking for the net charge, or when we are checking for the charge on the outer surface, we always consider the net charge. We consider net charge, Q net. Okay, what is my Q net? Say on one end of this outer plate, I have positive charge. On the other end, I have negative charge. So my Q net will be plus Q on the outer plate minus of Q. So what is my net charge on the outer plates of the capacitor? It will be zero. Okay. Suppose now I have to give another common doubt. So other common doubt, say if both the plates are connected with positive electrode, if both the plates are connected with a positive electrode, is my Q net still zero? Yes, exactly, Priyanka. So if I have a positive plate, say if I have two plates connected to a battery like this, now is the Q net on the outer surface of the battery or outer surface of the capacitor still zero? Is it still zero? This answer, no, Anusha, it won't be zero. So in this case, in second case, when we have two plates with same charges, say here also I have plus Q, here also I have plus Q. In this case, my Q net will be, what is my Q net? Net charge on the outer surface. Q net will be S2 plus Q plus Q. That will be plus 2Q in this case. Okay, it won't be zero. But when we have when we have something similar to this, positive charge and negative charge, so this is all negative, will purti negative irutte. In the other end we have all positive, then the net charge on the outer surface will be zero. Okay, outer plates will be zero. So that is the, this is the only case, this is the practical application of a capacitor. So we consider the outer plates of the capacitor, I mean outer surface of this capacitor will have zero charge or zero net charge. Actually, we should say zero net charge, but they say, I mean usually in general we say it's zero charge. The outer surface of the capacitor plates will have zero charge on the LGB. Understood, guys? I think this is understood. Am I going slow, or is it being difficult for you guys to follow? Okay, Abhishek. Abhishek, you have any doubt? Okay, Abhishek, you have any doubt? Like you said no. Okay, cool. Now, so one more representation. So how exactly happens? How exactly it happens? See, in general, we always say no, Hariprasad, no. When we connect two positive charges, polarization still occurs. Yes, okay, there exists polarization, but no electric field will be occurring. Okay. So, guys, yes, this is the application. So, this is how exactly when we connect a DC power supply, this is the exact way how my charge flows. Okay. So, always my only electrons can flow. ಯಾವತ್ತು ನನ್ನ electrons ಮಾತ್ರ flow ಆಗಕ್ಕೆ ಸಾಧ್ಯ. Always only my electrons can flow, but not the positive charges. Positive charges cannot move. Okay, only the electrons are free to move. So when we connect a battery, this battery provides an electromotive force. If you remember, it's the electromotive force. This forces the electrons present in the positive plates to push. This pushes the electrons present in the positive side of the plate. I mean, this end of the plate, and it will push to the negative end. So what happens? There is a net positive charge here. This net positive charge would create a net negative charge. You see, this side it will become bluish or reddish. Then this side it will become charged with highly negative charge. Then there exists an electric field between them. So this is called as the polarization of capacitor. Polarization of plates of capacitor. So capacitor as a device, we'll see the circuit symbol of capacitor is this. We'll have two parallel lines connected with two electrodes. Okay, so this is the circuit symbol of capacitor. And when we connect a capacitor across a DC, this is the DC representation. When we connect it with across an voltage source V, say if we connect across an voltage source V, so this capacitor, when it is connected here, the charges flow through this. And see, if C is the capacitance of this capacitor, the charges flow through this plates. Okay, it will store in, I mean there exists an electric field between them, and the electric energy will be stored between the plates of the capacitor. And usually there exists a dielectric medium. So if there is nothing present inside here, guys, I simply have two plates and there is nothing here. What will be in, say we are in Earth and there are only two plates, what will act as my dielectric here in this case? What will act as my insulator here? Air, exactly. So air will act as my dielectric medium. So it will be having a permittivity of epsilon naught, that is 8.854 into 10 power minus 12 newtons coulomb square per newton meter square. Okay, next, if I consider, so if I consider the capacitance of this capacitor as 2 microfarad and I connect a potential of 100 volts, how much is the charge stored in this capacitor? Guys, tell me how much is the charge stored in this capacitor? ಉದಯ್ ಏನ್ ಈಸಿ ಮಾಡೋದು ಸ್ಲೋ ಹೋಗಿ ಅಂತಿದ್ರ ಏನದು ಉದಯ್ yes guys, come on, tell me the answer for this. What is my q? How much is the energy stored inside this capacitor? Sorry, how much is charge stored in this capacitor? No, q is equals to c into v, that is 2 into 10 power minus 6 into 100, that is 2 into 10 power minus 4 coulombs, and energy stored is half cv square, that is 1 by 2 into 2 into 10 power minus 6 into 10 power 4. So this will be 10 power minus 2. Energy stored will be 10 power minus 2. Okay, 10 power minus 2 joules. So yes, correct guys. Come on. Next we have we use capacitor in various circuits. So as I told earlier, we use capacitor in a flash. So I told you guys, right? So we use a capacitor in a flash camera. Then yeah. So I try to explain you there exists an flash camera. So this is you might be knowing Nikon cameras. Those who were born are somewhere around 2000. Before 2000 might be knowing this. Even 2000 kids might know. I don't know how much you guys know. In ನೋಡಿದಿರಾ ಈ ಕೆಪಾಸಿಟರ್ ಯಾವತ್ತಾದ್ರು? I hope many of you might have seen this type of camera. So if you open this camera, see this is the flash which it has. So what happens? This camera will accumulate all the charges inside this capacitor, and when this shutter button is clicked, this will energize. I mean, this will allow. So it will take some time to click, right? I hope most of you might have experienced this. If you click on the camera, it will take some time for the flash to pop up. So what happens here is, so when they click the camera, this will start charging this capacitor in very drastic way. So this is some 230 volts 160 microfarad capacitor. Imagine how much charge is being stored. So this charge will be discharged at 1 second. At this amount of energy will be discharged across these two plates. This is again two plates. So there will be an arc generated, spark. There will be a small spark generated between these two plates. So this spark will be the flash, will become the flash for you guys. So this is the flash capacitor. Other than this, how many of you know this? Something like this. So what is this? What am I drawing here? What do you think this is? Yes, mosquito bat or fly zapper. So yeah, even your mosquito bat or fly zapper has a capacitor in it. It is an inductor capacitor combination. What happens? Some high amount of current flows through this. There will be a capacitor inside this, which will store energy. So there will be a battery, separate battery for recharging and stuff. So what happens? This battery, when you click, there will be a button here, right? If you when you click this button, what happens? This battery will charge this capacitor. Okay, there will be a high value capacitor. This battery will charge this capacitor, and on clicking that, when some mosquito comes and hits this, all the charges will be discharged between this net, metal mesh net, right? So all of them will be discharged over it, creating a spark. Okay, so that is the how we see the uses of capacitor. One more use in capacitors is, guys, most of you might have seen this. See, even when you shut down your PC, or even when you turn off everything, but still, say when you try to switch off and switch on your device, what happens? So there will be, see, all the energy. If something doesn't have energy to store in it, it cannot store memory at all. Okay, I think this would be a bit difficult for you guys to understand. So what happens? Say, yes, in a fan we discussed, right? In a fan we discussed in our earlier classes. Here, so we are going to discuss about capacitor inside a motherboard of a computer. So computer idiyala, our computer. So if you see the computer, even after shutting down, if you remove the battery also, it will save all your files. How is that possible? So if you remember the batteries of your capacitor, if you even suddenly remove your battery from laptop, or if you suddenly turn off your computer desktop, but still, once you turn on everything back, so sometimes you may see, sometimes if power fails automatically, all your saved files will be gone. But sometimes you can see that, most of the times you can see that all the unsaved files also still exist in your laptop. ಅದು ನಿಮ್ಗೆ ಇವಾಗ ಅರ್ಥ ಆಗುತ್ತಾ ಇಲ್ವೋ ಗೊತ್ತಿಲ್ಲ. I don't know whether you can understand right now. So yeah, there will be a temporary storage devices. So these capacitors will act as temporary memory storage devices also, and they also charge. So you could see there is some battery like structure. This battery like structure would provide enough energy for all the memory storage devices. These battery, this is a small battery. Actually, this is a small battery called the CMOS. So computer science student might know this. Those who have studied computer science, PCMC, PCMC area ತಗೊಂಡಿದ್ದೀರಾ, those people might know there is a CMOS inside your computer, even in your phone. Okay, every electronic device has a CMOS battery. So this is CMOS battery which energizes these capacitors. These capacitors in turn will give some of its charge stored to these ICs. These ICs will take the charge from capacitor to save memory. Okay, suppose if there is sudden power failure or something happens, even after some time you will still have that power, I mean saved files now. This is the reason. So capacitor can be used here sometime. So capacitors will be used here to as some memory storage devices also. So other than these, in our previous classes we also checked how capacitors can be used as radio controlling, I mean radio tuning devices and all, right? Okay, so these are the several uses of capacitor, and this is how a capacitor works. So in general, okay. Any doubts in this, guys? Capacitors, capacitor as a device. Any doubts in this? Please give me confirmation. If you have any doubts, let me know. Please click on yes if you have understood, or you could ask if you have any doubts. If you can, you can also ask. Okay, ಈ ನೋ ಸರ್ ಡೌಟ್ಗ ಅಥವಾ ಯು ಡಿಡ್ ನಾಟ್ ಅಂಡರ್ಸ್ಟ್ಯಾಂಡ್ ಅಂತನಾ? Okay, no doubt. Cool, cool, guys. Thank you. So next we'll go to combination of capacitors. First we'll study about series combination. Okay. So in combination of capacitors, say if I want some specific value of capacitor, say in market, that specific value of capacitor might not be available. So in next chapter, that is current and electricity, we'll be discussing about several circuits. of capacitors. So in those, I'll be discussing about the practical application of circuits. Okay, so ನಾನು ನಿಮಗೆ ಎಲ್ಲ practically ಹೇಳ್ಕೊಡಕ್ಕೆ try ಮಾಡ್ತೀನಿ. I'll try to explain everyone the practical approach of all these circuits. Okay, all the capacitors, resistors, inductors in practice, how we can use, where should we use, how to use, or what is the importance of them in our daily life, with the problem solving for your J mains and advanced and NEET also. So we'll be studying with series combination of capacitors. So why do we want to do series combination? Say for any circuits, say for any circuit building, I might require some specific value of capacitor. If I don't get that specific value, my circuit won't work. At that time, how can I achieve that exact value? So this is possible by combination of capacitors. Okay, so we'll be taking the series combination and parallel combination. Okay guys, come on, tell me what do you mean by series combination? What do you mean by a series combination? Guys, come on, reply. Series combination of capacitors andre ಏನು? So series combination means in general connection of one end. Say if I have some black box, so let there be some black box, A and B be the ends of this black box. Say if I have n such black box, each having A and B. Okay, so if I connect one end of this with the other end, say if I connect the B of B1, A1 B1, A2 B2, A3 B3. So let us consider these three ends. Say if I connect B1 of a device to A2 of the second device, then B2 of a device to A3 of the third device, then this combination where we have end to end connection, one end is connected to the other new end. So end of one capacitor is one after the other. Yes, exactly. So when we have connection one after the other for a system of devices, this combination is called as the series combination. Okay, so let us consider the series combination of capacitors. So yes, we have considered two capacitors. Let us consider two capacitors, C1 and C2. Let C1 and C2 be the two capacitors. So let V be the potential applied on the ends of these two capacitors. So I'll apply some potential V. So what happens when I connect this? Excuse me. So what happens when I connect this capacitor with potential V? What happens? The charge starts to build up across this, right? Say if V1 and V2 are the potentials, say total potential applied is V, the total potential difference applied is V, and if the individual potential drops, individual potential drop across capacitor C1 is V1, say capacitor C1, across capacitor C1, I experience a voltage of V1 volts, and across C2, I experience a voltage of V2 volts. Then, then, then what happens? Say if this capacitor is given with some potential, what should happen? Yes, correct, Priyanka. So the charge will start to build. Okay, the charge will start to build. Say if we have such combination of capacitors, this combination of capacitors can be replaced by a single equivalent capacitor. Okay, this combination of capacitors can be replaced by a single capacitor of equivalent capacitance. Say if C1 is the capacitance and V1 is the voltage across the capacitance, then a charge Q, say there exists a positive charge on one end of the plate and there exists a negative charge on the other end of C2. Okay, ಏನಾಗ್ತಿದೆ ಇಲ್ಲಿ? In this case, what's happening? My capacitor, the electric potential applied, potential difference applied, creates a net positive charge on one end of the plates of C1 and creates a my negative Q charge on the other end of the plate C2. Okay. Now what should happen, guys? So if this is having this plate is having a charge Q1, what should be happening inside this? What should be happening inside this? If this is plus Q on the outer surface, what should happen on the inner surface? So there exists a minus Q. Okay. If this is minus Q, what should happen in this surface? Inner surface of second side. If this is plus Q, this other side would be minus Q. If this is minus Q, what will happen to the other end? Yes, obviously the other end will be having plus Q. So this side, I should get a charge of minus Q. And similarly, if this is minus Q, inner surface will be having plus Q, other end will be having minus Q. So this will induce a charge plus Q here. So if you see, there exists a layer, there exists an isolated area between these two plates of the two capacitors. Say this plus Q and this minus Q can cancel, and this can be nullified. This as a whole can be nullified. So if I try to replace it, I'll get the equivalent capacitance between these two as the C equivalent. Now we know that the total potential drop across the individual capacitor is V is equals to V1 plus V2. Okay, so we know that V is equals to V1 plus V2. Now using this, also we know that C is equals to Q by V, right? Where Q is the charge on any one of the plates. Hold on. Now, if this is the thing, if we try to rearrange to get V from this expression C is equals to Q by V, if we try to rearrange for V, solving for V, what will I get? I'll get V as Q by C. Okay. So now what will I do? I'll substitute this value V as Q by C in this equation 1. Okay. So what will I get? We know V is equals to V1 plus V2. Substituting the value of V in equation 1, I'll get V is equals to Q by C1. So V1 is nothing but, what is my V1? This is V1 will be Q by C1. Similarly, V2 will be Q by C2. Then what will be my V? My V will be Q by C equivalent. So since in a series circuit, my total charge distributed on in a series circuit, remember this, in a series circuit, the total charge distributed remains the same, but only the potential varies. In series circuit, the charge distribution remains the same, but the potential varies. In this expression, I know that the charge on the left hand side is equals to the charge on the right hand side. So I can cancel these charges. Excuse me. Now, this equivalent potential or this equivalent combination, this can be written as 1 by C equivalent is equals to 1 by C1 plus 1 by C2. So this is the combination. So this is the expression for the capacitance, for the effective capacitance of two capacitors connected in series. Okay. Yes, exactly, Dhanush. So now if I have n such capacitors, say if I have n such capacitors, then the capacitance can be given as, say if I have C1, C2, C3, etc. Cn, if all the value is C, if all has the same value, that is C, then the net capacitance C equivalent 1 by C equivalent can be given as what? How can we write that, guys? 1 by C equivalent equals to 1 by C1 plus 1 by C2 plus 1 by C3 plus etc. 1 by Cn. This can be written as 1 by C equivalent is nothing but summation of I times of 1 by Ci. So this is the general expression for the capacitance connected in series combination. Hope this is understood, guys. So this is the expression for capacitance connected in series combination. Say further for two capacitors, only for two capacitors, I can try to simplify the C equivalent as C1 into C2 divided by C1 plus C2. So if you try to cross multiply and take the LCM, you would get 1 by C equivalent as C1 plus C2 by C1 C2. Here, my C equivalent will be C1 C2 by C1 plus C2. Okay, this is the expression, general expression for the capacitance or combination of capacitors in series combination. Hope this is understood by all. Yes, guys. Please reply with yes if you have understood. Yes. Okay. Cool, guys. So next we'll go to the parallel combination of capacitors. So what happens in parallel combination? So let us consider two capacitors. Let C1 and C2 be the two capacitors. So these two capacitors are connected in parallel. So what do you mean by parallel combination now? Say if I have the same ends, say if I have A and B across these two capacitors, if I have same ends connected to the same ends of the capacitor, if I have similar ends connected to the potential in the same, I mean, say if A is connected to A and B is connected to B. So what happened in series combination? A was B was connected to next A, then this B was connected to the next A, right? So this was series combination. But here in parallel combination, the same type of charges or same connection, A will be connected with A, B will be connected with B. So such combination of any device is called as the parallel combination. So in parallel combination, potential remains same. So in series combination, what remains same? Charge remains same. Here potential in parallel combination, potential is same, but charge is varies. My charge only varies, but potential remains same. So if V is the potential across this combination, then V will be the potential across the capacitor C1, and V will be the same potential across the combination across the capacitor C2. Then if I say that the charges Q1, let Q1 be the charge on C1 and Q2 be the charge on C2. So Q1 and Q2 will be the charge respectively on C1 and C2 on the positive plate. So it's given by plus Q1 and plus Q2. Similarly, on the negative plates, if we have minus Q1 and minus Q2. Okay. Now these two combinations of capacitance can be replaced by a single capacitor of equivalent capacitance C equivalent, which has the total net charge plus Q and minus Q on the plates. Now this can be given by plus Q, or Q is equals to, say how can we write the general expression for charge stored, guys? Tell me. Q, total charge Q is equals to, can I write it as Q1 plus Q2? Can I write total charge Q is equal to Q1 plus Q2? Yes. Yes, in parallel combination, the voltage or potential across the plates of the capacitor will remain same. Tanush. In parallel combination, the potential applied on the plates of the capacitors will remain same. In series combination, charges remain same. In parallel combination, potential remains same. Okay. So, Q is equals to Q1 plus Q2. So in this case, my net charge, total charge, if Q is a total amount of charge given by my battery, and Q1 and Q2 are the respective charges stored on the individual capacitor C1 and C2, the total charge is then given by Q is equals to Q1 plus Q2. Okay, now, yes, we know C is equals to Q by V. From here, we can write Q as, what can we write Q as? Q is equals to C into V, right? From here, we can write Q as C into V. Substituting this equation, then we'll get C into V. Say here, my C into capital Q is nothing but C equivalent into V. That is equals to, what is my Q1? It is C1 times V plus C2 times V. if you see in this expression, in all three cases, I mean, in left hand side as well as right hand side, my potential value of potential is same. So what can I do for potential? I can cancel my potential values. Then the final expression which I get is C equivalent will be equals to C1 plus C2. Okay, this is the general expression for combination of capacitors in parallel. Okay, so in parallel combination, my C equivalent is C1 plus C2. So if I have n such capacitors connected in parallel, so if I have n such capacitors connected in parallel, so C1, C2, etc., Cn connected in parallel across the common potential, what can I write my net capacitance as? What can I write my C equivalent as? My C equivalent will be equals to C1 plus C2 plus C3, etc., up to summation of Cn. So this is written as C equivalent is summation of I times of Ci. Okay, this is the general expression for the capacitance of capacitors connected in parallel. Correct. Add all capacitors. Okay, understood, guys? So this is the combination of capacitors in parallel. Okay, please click on yes if you have understood both series and parallel. Everyone, please click on yes if you have understood both series and parallel combination of capacitors. Yes, cool. So take this as a homework, guys. So please take this question as a homework and try to answer this. We'll try to solve this question in tomorrow's class. Please take this screenshot, okay? Please take its screenshot and try to solve it as a homework. Or if you can solve now, it would be good. Okay, try to solve now also. Okay, so this is so in today's class we studied about electrical energy density. So we studied about electrical energy density, then we studied about the derivation, then we studied about capacitor as a device, and we saw where are the different cases where we use the capacitor. We saw how capacitor works, and also we learned about the circuit symbol of capacitor and DC analysis of capacitor. Then we studied about the series and parallel combination of the capacitor and the effective capacitance of capacitors so far. So we'll try to solve few questions based on this, and in upcoming class, so in the next class we'll be starting with dielectrics. Okay, so how introducing a dielectric would affect the capacitance of a capacitor, we'll learn about that in next class. Okay, all of you try to come prepared to that. Okay, so guys, hope guys learned, had good time. Okay, so we'll meet again in our next class. So if you have any doubts on any of the part of the capacitors, if you have any particular doubt to ask, you could ask now. Please try to ask all the doubts if you have. Okay, okay, thank you, Anusha. Hope guys, YouTubers, you also understood everything, every part of it. So if you have any doubts in any ways, any parts of this capacitor, you could ask me. Okay, thank you, Manohar. Thank you for being in class. Super. So how many of you like electronics, guys, by now? So is there anyone who like electronics too much? So how many of you like robotics, robots, electronics? Okay, Manohar, hi. So I think Manohar, have you been? I mean, when I was in DK, did we meet? I don't know if we had met Manohar. Cool. So yeah, guys, if you have any doubts regarding any circuit problems or any uh, physics problems, you could approach me. Again, Priyanka, no, I don't have any information about JNV's reopening right now. So as far as I know, JNV's in the school where I'm currently working, there was a rumor that it might start on December first week or January first week, but I don't know. We don't have a proper information about that. Yes. So yeah, again, guys, this is one important notice. So yes, please start preparing for your J mains if you have not yet started. Start revising. I hope yes, your J mains exam might be scheduled on February. Maybe it's still a maybe. There is no official notification yet anywhere. Okay, we have to check out that. So when is it would be obviously in March, I guess. Kiran. March time nale irutte ಅನ್ಸುತ್ತೆ. I guess it might be in yeah, March. Any other doubts, guys? Any doubts? So I think application for JE is not yet started, Lakshmi. Once it started, we'll notify everyone. We'll explain everyone how to apply, and we'll make you apply. Everyone will write J means at least the first exam. Okay, everyone, irrespective of if you are a JE aspirant or not, you will be applying for JE first exam, at least for the January February exam. You will get an idea how what are the different types of questions you may get in your other competitive exams which you are targeting. Okay, okay, guys. Yes, we will, Devikarani. That's why we are here. Yes. Okay, guys. Then we'll wind up for today. Then please try to solve this question and come to the next class. Okay, we'll discuss that. Uh, Good question, Manohar. Thanks. So my name is Pradeep, Program Associate for Physics in Avanti Fellows. Uh, yeah, we'll inform Lakshmi. Cool, guys. Then we'll meet again in our next class. Bye bye. Have a nice time.